volume of this series of presentation on data science for dummies. I'm happy to present Dan Assouline. It's a PhD, was a PhD in civil engineering from EPFL and a master's degree in civil and environmental engineering from the University of California, Berkeley. After a postdoctoral position at EPFL, Dan joined our team in June 2020. So that's already more than 1 year.
More than a year ago. Yeah.
And before that, he worked as a data scientist, data analyst in research at the Research Center in Berkeley, and as a teaching assistant for statistics and physics classes at Berkeley and EPFL. So today, Dan presents, so I said, the volume 2 of DS for Dummies, which will be about, well, it's a 45 minutes presentation, yes, on concepts about machine learning. It's an introduction to machine learning, and maybe just to demystify this black box of, yes, machine learning tools and confront this to statistical theories. So thank you, Dan, for the presentation. And just about the question, you can ask questions during the presentation, and if you have some questions, you can put it on the chat for those who are remotely assisting to the presentation. And in the room here, you can ask whenever you want. So thank you, Dan.
Okay. Thank you very much, Mayan, for the introduction. So yes, thank you all for being here, those who are here and those who are on WebEx. And welcome to the second installment of our Data Science for Dummies colloque. I'll be talking about machine learning concepts and frameworks and its relationship with statistics, classical statistics analysis. So what is the goal of this session for you? To have a general view on machine learning, to understand the main concepts behind it. You know, it's not magical. There are like some really basic principles behind it. Get to know the basic frameworks and tasks that you can do within machine learning. Get motivated to know more about it, because obviously in 45 minutes I won't have time to present, you know, everything. So I'm here to give you an idea about a lot of concepts behind, and know where to start to look about it if you want to. And finally, understand the basic common grounds and differences with traditional statistics, as it's usually what people wonder at some point with relationship to machine learning. So that's the outline. So first we'll see what is machine learning. And then we'll go through the different frameworks. So we'll talk about supervised learning, the idea, tasks, and some important concepts, notably model selection and evaluation, which will be used during the training phase of supervised learning. Unsupervised learning. We'll go through quickly a third framework, which is called reinforcement learning, just to give you an idea. I will be fairly quick on this one, but it's just, you should know it exists because it's quite used. And finally, I will compare machine learning and statistics and show you how it's actually complementary. And finally, I will summarize. So what is machine learning? It's artificial intelligence. So it is actually a subdomain of artificial intelligence. The problem is that, you know, in the last 5 to 10 years, we've seen it in so different many places, and we don't really understand what it is, and it's almost quite frightening. You know, it's like robots, films, a lot, you know, talked about artificial intelligence. This one is quite old, actually. You know, will machine beat humans, etc. Big data, of course, is something we've been talking about for so many years, and a lot of people don't really know what it is because it's not really clearly defined. And at the end, you know, you have just like a bunch of words that are floating around and that some people use kind of indifferently because the topic is a hot topic, because machine learning really works. So you will see here and there a lot of different words: artificial intelligence, data analytics, data mining, deep learning, pattern recognition. Some of these terms are redundant, and some of these terms are actually subdomains of other terms. Then you have, of course, big data. What is big data? It's really just, it's kind of a paradigm of the huge amount of data we have, trying to take advantage of the huge amount of data we have. That's all big data is. But to say that you do big data, yes, to say that you do big data is something a bit special. So, for example, an economist called Dan Assouline in 2013 said this: big data is like teenage sex, everyone talks about it, nobody really knows how to do it, everyone thinks everyone else is doing it, so everyone claims they're doing it. This is kind of, you know, nowadays data scientists are kind of mad at this because everybody was saying it at some point. For big data, it's kind of true because, you know, it's a very broad term and it's very weird. So we need to define a bit more things. A simple hierarchy remains. Artificial intelligence is the big domain of trying to give some intelligence to machines. Then you have machine learning, which is basically an ensemble of algorithms to teach machines how to learn. And deep learning is a sub-genre, a subdomain of machine learning of methods, okay? And then data science is kind of a mix of the three, just trying to analyze some data and finding some patterns, okay? So what is data science? This is a bit of overlap with Titre. It's supposed to be a mix of computer science, math, statistics, and domain knowledge. You should know about the domain you're working on, otherwise it might not make sense, okay? And then depending on this, you have, you know, machine learning is kind of a mix between computer science and statistics, etc. So this is generally true. But you must be careful with the definitions you give, and I will show you at the end the different types of jobs related to this. It could be confusing. So what is the goal of machine learning? Okay, from a set of measurements that we call data, you learn a model, possibly without an a priori on the shape of the model. You want to learn directly from the data to understand and predict a phenomenon. That's really the base of machine learning. So at the end, a quite clear definition of machine learning is an ensemble of algorithms that improve their performance with experience. So you feed them data, you feed the algorithm data, and it will get better and better based on the data you feed them. And feeding the model corresponds to training the model. Feeding the model some data corresponds to training the model. You give the model as much information as you can so that it can recognize patterns with new data you will give to it. A simple example in 2 dimensions. So let's say you have a set of animals characterized by weight and fur density, for example. You want to learn a classification function, so this will be the model, to classify animals between tigers and lions. So let's say you have 100 lions, 100 tigers. You have their weight and their fur density. Just based on these 2 variables, you try to say, okay, this is a lion, this is a tiger. This might not work, but it might be discriminative enough so that you can make the classification. Another example, let's say you have a population of patients with speech characteristics, the speech volume, how loud they talk, and the speech rate, how fast they're talking. And let's say you want to, again, build a classification function to detect patients with or without Parkinson's syndrome. Since the speech rate and the speech volume are symptoms of Parkinson's, you might be able to try to separate, to classify between patients with and without the syndrome. So let's say that we give a toy example of translating this into data. So let's say you have x1, which is the rate in the x-axis here. x2 is the speech volume, how loud they're talking. And then you have classes, so you know which points are which ones. These points are patients without the syndrome, and these points are patients with the syndrome. It seems that people with the syndrome have quite a fast rate. They speak fast and they speak with low volume, whereas the people with no syndrome is the contrary. They speak quite slowly and with high volume. Okay, so let's say you want to build a function that classifies between these 2 groups. It's quite easy because they're separated quite well. So a good idea would be to just draw a line between them and to maximize the space between the 2 groups. That's actually a basic idea of a very famous algorithm called super vector machines that I will show you in the next presentation. But the problem is, of course, if you don't have that separation between the 2 points, you might not have a linear separator that is possible. So in this case, you might want to use more algorithms that are nonlinear, especially a lot of machine learning algorithms can do that. So that's just an example. So which are the frameworks that we have in machine learning? The first example I gave you was an example within the framework of supervised learning. We say that it's supervised because you have what we call the labels. So the data is labeled, meaning that you have examples of the output. In this case, you know which patients have Parkinson's syndrome and which patients don't have Parkinson's syndrome. It's just specified by the colors, basically, on the data. So you can learn from the examples you have. In unsupervised learning, you don't have the labels, so the data is said to be not labeled, which means that you do not know, let's say these are also a population of patients, some with Parkinson's syndrome and some without. You don't know which are which, but you can try only with the distribution of the features of the variables, try to make some groups. This is called clustering. It's one of the main tasks, and we'll talk about it. A third and interesting framework is called semi-supervised learning. And I won't talk about it in a lot of details, but it's just, again, it's interesting that you know that it exists. It's basically the case where you have data that is partly labeled. So you have a lot of points, a lot of, a big population of patients, for example, but only, you have examples for only a very, very few, a very small number. So let's say you know that 3 patients have the syndrome and 3 patients don't have it. Well, it turns out that if you try to do supervised learning, you may end up with a classifier like this. But if you use the rest of the points you have, it might help you to guide you into doing a better job at classifying. So this is the field of semi-supervised learning, but it doesn't always work very well. So I won't talk about it. It's a bit more difficult. A last and fourth framework is called reinforcement learning. And reinforcement learning is really like a die and retry approach. So you're creating data by doing experiments on something. You're basically trying and see the result you have. If it's good, you keep doing that and you go in that direction. If it's not good, you kind of go back and do something else. And the more you do experiments, the more you learn the patterns. And this is actually very interesting for robotics, for example. And I will show you a few examples. Basic vocabulary, also because some of the words actually refer to something you know already in statistics, but they are slightly, the vocabulary is just different sometimes. So obviously the data, just measurements of points, this you know. We call features the input variables. So what we call in statistics predictors or independent variables, usually we call features in machine learning. It's just a cultural thing. The target is the output variable. So it might be a categorical variable, for example. The samples is the values of the features. The labels is the values of the target variables. So it's just 1 and 0, for example, if you have 2 classes. And we say that the data is labeled if you have the examples of outputs. So this we've seen already. And finally, to train a model means to build a prediction function based on that data following a particular ML algorithm. When you train the model, you build the function to be able to predict later. Okay, so this is basic algorithm, just basic notions. So we go into supervised learning. So what is supervised learning? Again, it's a framework where you have the labels. You know the classes. You know which patients have Parkinson's syndrome and which do not have. So what does training a supervised model means? Well, formally, it means this. You have features. You want to train a function phi, so that phi of x equals y. Well, it turns out, say that simply, it's just you want to build a function which maps known inputs that we usually call x, it's like a tradition to call it x, to known outputs y as close as possible. So basically, you have your features, so you know patients which, again, have Parkinson's syndrome or not. No, I'm sorry, you have the speech characteristics, you have the examples of which do not have, and you want to build the link between the two. It's the function, it's phi. You want to build a function so that when you apply the function to x, you obtain what you have in y. So this is really what machine learning does, really trying to predict. And the type of labels will give you the type of the task. The type of output variable will give you the type of the task. So if the outputs are real numbers, basically any value, all possible values, it means that you're doing regression. Well, for example, here you're just doing linear regression. So the gray points, you're trying to fit a line, let's say it's linear regression. You probably heard of this before. You just have your y here and your x. You're trying to fit a line. Okay, so you're trying to follow the points, and it can be any numbers. If the outputs are integers, so a limited number of discrete numbers, so 0, 1, for example, if you have two classes, it's called classification. It's the only difference. So let's say, again, our example, this was a classification example. Okay. What is the final goal of supervised learning? It's what we call generalization, which is basically the ability for the model to predict outside of the known labeled data for all possible points. So you have your data where you know everything, you know X, you know Y, the inputs and the outputs. You want to train a model that, again, maps X to Y, but you want to train it in the way that if you bring new X's, I will give you the right Y. Otherwise, it's useless. In your little world, when you know everything, it's good to have a good function, but if it doesn't generalize to the outside world, it's useless. So what we do here is build phi to minimize this ugly mathematical function, which is just the prediction error. It's just what we call the expected prediction error. Why am I showing you this? It's just because this here, this L of y phi x, is an important notion called the loss function, which is basically a function that measures the error between the y and the x. I mean, between the prediction you do and the actual output you have, okay? And you can choose this function. Based on the function you choose, you will have a different algorithm. So, for example, this is squared loss. It's what we use in typical linear regression, okay? The problem is this quantity here is a probabilistic quantity. You cannot have the real one. You cannot have it. So what you do is you use a typical training strategy, trying to approximate this error with test sample estimate. What you're going to do is you're going to simulate the outside world, basically. You're going to simulate the outside world, but you don't know anything, by taking out a portion of the data you have, and you're taking it away. You don't train on it, and then you test your model back on it. So what you do is you separate the labeled set, is the set where you know everything. You take 75% for training, and 25% of the data, you just put it away. You train a model on the training set, and then you take back the testing set, which didn't see the training data, and you predict, you do prediction on this test set, and you measure the error between the prediction and the actual values of the outputs, because you know these actual values. Okay, a very important concept is what we call bias variance trade-off. So when you have your prediction error, basically which tells you the performance of your model, you can decompose it in 3 terms. A noise that you don't control is just, there will be an extra error that you cannot control. A bias to the square, but it doesn't matter, and a variance. So what is the bias? Is the distance to the true mean, which is basically the average of the real function. Let's say you have a pattern, you want to approximate a function. It's just the average of the true function. It's how far you are from the true function, and the variance is how spread you are around the true function. So a famous analogy we use to describe this is targets. So let's say you have targets. The reality is the red part. It's the function you want to approximate, the function you want to learn. You have the variance is how close you are to the center, and the bias is how close you are to the center, and the variance is how spread you are. So in this case here, the top left one, you have low variance and low bias. You're concentrated and within the truth, basically the center. And if you have high bias and high variance, you're far away and you're spread. Okay, so
just one quick question for
yes.
understanding. What's the difference between noise and variance?
Oh no, but what I call noise here is just an irreducible error. It's not a variance. It's just the variance here is related to the prediction you do. Is how you know the amount of range you touch when you do a prediction. The noise, what I call noise here, is really just an irreducible error based on the data you have, based on a lot of things you cannot control. So it's just
anything like a random variation would not be a noise. It would translate into variance.
Yeah.
And so noise is, that's the point where I was a bit lost. So what's noise? So noise is
it's just
it's not related to
variance.
random error.
No, I mean, well, it's really it depends what you call random error. It's really the part of the error which you do not control, which depends on the data you have, which depends on what you want to predict, which depends to, on the type of algorithm you use. It's really, you cannot, basically in algorithm, you will try to either reduce bias or reduce variance or both. But this one, you cannot control. The noise will always be here. It's just, it's just saying on top of the error, you have this that you cannot, it's kind of like a safety, a safety net. There's something that you cannot control in any case. Okay. So actually this trade-off, you control it with the complexity of your model. So basically, if you do like a 101 economics graph, you have the complexity in the x-axis and the error in the y-axis. This line there going down is the bias. If you make your model more complex, you will decrease the bias. You will get closer to reality. But the problem is you might increase the variance because you try to be everywhere. And basically the best thing to do is to try to be at the intersection of the two so that you have kind of low bias and low variance and you have the optimal complexity. What will happen basically, let's say you have a typical regression that you want to do, you have these points. If you have a bias that is too high, you're far from reality, so you just have something that is too simple. If you want to get stuck to the points too much, you have too much variance. So in this case, the variance is too high, and it will be just wiggly. If I give you new points, you won't have the good value. And the optimal is in the middle, where you follow the points, but you still keep the variance to a lower level. Okay, so that's really what happens. And basically, when the bias is too low, you say that you underfit. When the variance is too high, you say, bias too high. And when the variance is too high, you say that you overfit. You're trying to get stuck to the training data too much.
Yes, isn't the error, the noise linked to the optimal? You don't have all the important predictors.
Yes.
It's just the source of the noise.
Yes.
Whereas the variance will be reduced when you increase the sample size.
Mm-hmm.
And actually, noise is just the lack of a relevant important predictor.
Okay.
In this case, isn't it?
Right. Yeah. In this case, yes.
So in the case, in the sense,
yeah.
optimal.
Yes, I see what you mean. Yeah. In this case, yes. But this is a very simple example. But yes. So then another important concept. It's called model selection. So basically, it's how you choose your hyperparameters of the model. So in machine learning models, even if they're not parametric in the way that you usually say for statistical models, like for example the betas that we call parameters, here we call it hyperparameters to differentiate that from betas, from weights. It's just extra values you have that are just constants that you choose that tweak the model in certain ways. So there are multiple ways to do that. For example, a very famous way is called k-fold cross-validation. Well, you try with grid search, you basically try a range of different parameter values, hyperparameter values, and you see what it gives you as an error in the training set. So the first thing you do is the grid search. So let's say you have a model with two parameters, gamma and c, and each point gives you the error in the training set when you choose these two values. Okay, and you can go through all of these and see basically what's the best setting of parameters. But to make it better, instead of just doing that in the training data entirely, what you can do is you can separate the data into k-folds. So for example, in this example, you have 7 folds. And what you will do is you will train with different portions of the data and test with the remaining part. So let's say you train on 6 portions and test on the remaining part. And if you do this, all the permutations, it just gives you more heterogeneity in your data, and you just see more patterns. So at the end, you have a better estimation of the error given by the parameters. This is exactly what I just said. So, and then at the end, you choose the parameter that minimizes the error in the training set. Okay, after you selected the right parameters, you need to assess the performance of the model. So this is called model evaluation. what you do is basically measuring the discrepancy between the predicted outputs and the known outputs in the test set where you didn't train. An important thing is you must compute the training error also. So do the same, you can apply to inputs, but in the training set, to compare with the testing set to see if there is overfitting or underfitting. So this is really important. Usually, a good way of detecting underfitting is if the training error is very high, so obviously you're doing something wrong, you're too far from the truth, and the training error is the same as the test error. But in the contrary, if your training error is very good, so it's very low, it means that, okay, you're doing a perfect job in the training set, but probably you're too close to the points of the training set. And if the training error is much lower than the error in the testing set, it means that you don't generalize well, so you overfit. You're getting too close to the points of your training. Usually, it's a good sign when the training error is just slightly lower than the test error. It should be lower, but slightly. And there are many metrics to evaluate this discrepancy based on the task. If you do classification or regression, there might be different metrics. So for regression, basically, you're really trying to measuring the value difference between the prediction and the outputs, and the known outputs. And in classification metrics, basically, you will count the points that you classified well, very easily. So first, as a classification matrix, this is a very classical things we do when we do classification with two classes. So this is called the confusion matrix. You have here the actual values, so the actual classes. Let's say, for example, 0 is without Parkinson and 1 is with Parkinson's syndrome. And here you have what you predicted. So here, this is the number of points that you well classified as 0, so it's called the true negatives. And then the same principle, you have the true positives, the false negatives, the false positives. The point that you classified as positive, but actually they are negative. So it gets a bit, you can really get a bit confused into positives, negatives, false. Now, the thing is at the end, you can just use these numbers to extract some performance. You might want to know how many points you classified well, or you might want to know how many ones you classified well, or how many zeros you classified well. And these give you different kind of performance metrics. The accuracy is the most famous one. You just have true positives plus true negatives over everything. This just means the number of total classified points that are well classified over the total number of points, okay? So you just have a rate of how many points you classified well. Another very used thing, it's called the ROC curve. So it's the receiver operating characteristics. I think it was actually created in Second World War. That's why it has like a weird name, to detect between signal, radar signals, sorry, and just noise, just random noise. The idea is simple. Basically, when you have an algorithm, usually you have probabilistic outputs. It won't give you exactly, okay, this is a 1, this is a 0. It will tell you there's 60% chance that it's a 1, 40% chance that it's 0. The thing is, with these probabilities, you can decide the threshold you take to say, okay, it's a 1 or it's a 0. Usually you take 50%. If it's more than 50%, 60% percentage that probability that it's a 1, you say it's a 1. Well, this curve is basically the curve where you change this threshold. You make it move and you have different points. And you show the false positive rate versus the true positive rate, which is here. And at the end, the higher the area under the curve, the better the performance of the model. It tells you that when you change the threshold, it still is good. And you can take, at the point, the Pareto kind of front, which is the optimal point. And if you want to have a strict threshold or more lenient threshold, you may take somewhere else. Okay, so this is the ROC curve. It only works if you have two classes, so in binary classification, otherwise you cannot really do this. So let's say you build your model. So you have your classification model, it's called phi, and it's this. It's just a linear line in this case. Okay? So what you do when you have new points, to predict the new points which are gray, you just say, okay, if it's on this side, it's an orange point. If it's on this side, it's a blue point. Okay, that's really what classification is. you might have more difficult models or much more data, but for this type of classifier, that's what it is. Okay, for regression, you have a lot of different discrepancy functions. You don't have ROC curves anymore. A lot of functions. This is annoying because you don't really know what's the pred and observation, but actually at the end, all it does is just taking the discrepancies, prediction minus reality, and normalizing in different ways to see how far you are from the truth. So this is really a type of regression metrics. Okay, we go to supervised learning now, and it will get a bit simpler because there's less things or fewer things you can do actually. Let's say we go back to our original example, but you don't have the outputs. So the data is called unlabeled. You don't know which people have Parkinson's syndrome and which people do not have Parkinson's syndrome. Well, in this case, what you can do is you can still tell that these are two different groups. So it might seem that actually one group is the group with Parkinson's syndrome and the other one is the one without. You don't really know which one. You can go within and see the characteristics to know which one. But at the end, you know, you can try to find some groups. If it's like this, it gets more complicated. And that's why you have a different kind of algorithm. So unsupervised, again, is to define it clearly. You don't have the labels. So there's no truth to rely on. The learning is very different. And there are two tasks that are mainly possible. Either clustering, that's what we said. You try to find clusters only based on the features. Either dimensionality reduction, which is just a method that reduces dimension. So let's say you have this S in 3D, you try to apply a method that reduces it in dimension so that you can see more things. If you have dimension 10, you cannot visualize, so it might be helpful to do this. And the subdomain of nonlinear dimensionality reduction is called manifold learning, and it can get very complicated. It's very interesting, but it's very, very mathematical. So what is clustering? Basically, given some data where you don't have the outputs, so it's unlabeled, you want to find groups of points which are similar to each other within the same group and dissimilar to each other with respect to the other groups. This is clusters. Again, there's no truth to rely on, so there's no systematic steps for the model evaluation. So what do you do for selection, for evaluation? Well, what you can do is first visualize. So if it's in 2D or in 3D, you should do it because you might see actually clusters already. If it's in higher dimension, you might want to use dimensionality reduction to help. And you must use expert knowledge, so basically see within the clusters after you extracted it to see if it makes sense, if it seems that actually the features are very different and if they're coherent with each other. And finally, there are some metrics that exist as an indication of good clusters. For example, the silhouette coefficient would tell you how close they are to each other and how far they are to the others. And there are many different coefficients like this. It's guides, but it's still useful. What is dimensionality reduction? It's, again, you try to reduce the dimensions, but trying to keep properties or structure of the data at the same time, so that you can visualize better, but you still have the same structure. Otherwise, you lost a lot of information. So this is useful to visualize. This reduces the computational burden before analysis. If you have a giant data, it might really help for you to reduce the number of dimensions. You can potentially find patterns that you didn't see until now. And if you're really lucky, you can almost find clusters already. So again, taking the same S example, you have different algorithms that reduces. This is just an example taken from scikit-learn, which is a famous library which I will talk about in the next session more in detail. This is another example of handwritten numbers. It's called MNIST data, where actually each of these points here are handwritten numbers, and when you apply a certain method called TSNE, it already gives you, groups. The color here tells you how well, which color, each color is a group. So actually, just by reducing the dimension with this method, it already gives you groups. So it can be very useful to use this kind of methods. Okay, what is reinforcement learning? So again, it's a die and retry approach. So what does it mean? It's that instead of having inputs and correct outputs, like you have in supervised learning, in this case, you have inputs, you have some outputs, it's not the labels, and you have a grade for the outputs. you know if you're going in the right direction or not. So, and the goal is to try to maximize the reward in the short term, but more especially in the long term. So basically, what you do is you try many experiments, and you create some output with the experiments like this, and you attach a reward to it, and you just die and retry. And the more you get in the right direction, the more you get better. This is good for skill learning, behavioral learning applications, like robotics or personalized medicine. Usually you have this kind of framework where you have an environment and a reward given by an agent. It's exactly what I said. So it's really used in chess, for example, where you have initial positions. So the algorithm may try all kinds of initial positions and all kinds of moves and see if in the long run it gives you a better result or not. This is really used nowadays in chess, and it's very powerful. It's much better than the world champions. And then pancake flipping is another example. So just a few seconds of a video where basically a robotic arm is trying to learn how to flip a pancake. So as you can see, it's not very good at the beginning, but it will get better. It can take 100 trials. This one is very. But after a few trials, basically taking motion sensor, but after a few trials, it manages. It basically learns that it shouldn't throw too high or too fast, and then only 50 trials and it gets there. So, and this is really used in robotics. It's like everything. Reinforcement learning is everything in robotics. Okay, so finally, machine learning and statistics. So I've heard a lot, and I'm sure you heard it too, that machine learning is just a new name for statistics. It's just the same thing, but it's hot. So we say that we do machine learning, but actually we do statistics. Or a little more refined, machine learning is glorified statistics. It's just, with sugar on top. It's just a bit better. It's the same. So you have a lot of memes like that, for example. You put a frame, statistics, it's machine learning. You do linear regression, it's machine learning, whatever. Okay. The thing is, it's not true. Okay, so where does that come from? Of course, they have common grounds. Okay, they have fundamental probability notions at their base, of course. And they want to learn from data and possibly make predictions. Okay, but the thing is, it's not enough to say something like machine learning is glorified statistics, because otherwise, physics would just be glorified math. You never asked physics why, you never asked to justify itself. It uses math, it basically expands on math to, describe the world. But it's really using math, but it's a different domain. It just expands on top of it. It's exactly the same thing with machine learning. They're both really useful, but they're doing slightly different things. Their aim is not exactly the same. So in this case, what is the goal of statistics? What is the main goal of statistics? It's to characterize the relationship between the data and our outcome variable. So this is called inference. You might want to answer questions like, is this vaccine effective? Which genes are associated with prostate cancer? For a question like that, statistics will be the way to go. Even though it was created a long time ago, it was really designed for that. The goal of machine learning is a bit different. You learn from data, but the idea is really to try to make the most reliable and precise and repeatable predictions. So you want to do prediction, basically. You don't really focus on the inference. So you want to do something like disease evolution prediction, or you want to try to detect tumors with image processing. Of course, they overlap. If you have a statistical model, you can always predict, and machine learning models are not, black boxes. You can still, depending on the model, you can still, extract confidence intervals, you can still infer a lot of things on the variables, but it's not designed for it. The main goal is to predict. Okay, is that the only difference? Well, not really. I mean, this difference comes from the real difference, which is the base of the two domains. So statistics is based on probability theory, only in probability theory. Then it derives everything from it. Machine learning is based on another theory that builds upon statistics, probability theory, which is called statistical learning theory, which was developed in the 60s. So it's quite an old theory, actually, which expands upon classical statistics. So for example, yeah, I put a lot of memes in there. Statistical learning theory is indeed a mix of computer science and statistics. So, you know, it's this. The problem is, it can get very complicated. So yeah, I have way too many memes, but yeah, I like memes. This person is actually a very famous machine learning professor in Stanford called Andrew Ng. He's like one of the gods of deep learning. And you know, he's protecting the student from all the math behind, because there is a lot of math behind, and you might be tempted to just use MATLAB to just, you know, plug a deep learning model and do some things, and it can work. But you know, the more you get into it, the more you know the math, and you get better at it. But it is actually technical. To give you an example, supervised learning actually, theoretically, formally, it's what we call empirical risk minimization, which is the following in a nutshell. What is the expected risk? Remember, I told you, I showed you the prediction error before, the expected prediction error, but this is like an advancement on that. It's you basically sum the loss function, which gives you the error, times the true probability of the variables you have, which you don't know, and you basically estimate this with the empirical risk, where you replace the true probability with the probability that generates the data. And this gives you basically the test prediction error. So that's why you need to separate between train and test. The entire statistical learning theory, and again, it can get very complicated, is designed to optimize predictions. Then on top of it, you might want to infer things, you might want to interpret, but this is really what it's designed for. So these are some general, it's not always true for all the models, but these are some practical differences. Usually a statistical model will try to model the data generated in the process. Machine learning will try to learn directly from the data at hand. For statistics, it has identified unknown parameters. For machine learning, it might not impose an output predictor structure. With statistical model, you will compute p-values and significance tests, confidence intervals. With machine learning, you really validate the model with the test set evaluation. Similarly, you look for robustness and significance of parameters in statistics. For machine learning, you want to be as good as you can on the test, again, on the test set. You really want to optimize the prediction. You look for a closed form solution often in statistics, whereas you try multiple models based on the loss function that you chose in machine learning. So you see the aims are a bit different, but you know, they work towards the same goal, basically, depending on what you want to do. So why is machine learning so famous nowadays? Well, because you have more data, and you can do statistics with a relatively small amount of data, but machine learning, depending on the model you're using, it's very, very hungry on data. So because you have more data, it works better nowadays than it used to do before, and you have much more power. This is a typical graph of the Moore's law, which gives you the increase of power of the computers with time, and this continues. So because you have power and more data, things like neural network, which was created, you know, in the 60s, 70s, didn't really work at the time, work now because you have a lot of data and a lot of power. And because ML is designed to take maximum advantage of this gigantic amount of data, then things really work well nowadays, especially with deep learning. So which is the best between statistics and machine learning? Of course, it's stupid to ask this question. You just choose based on the goal. Depending on the size of the data, if you want to do inference or prediction, if you want to isolate effects of special variables, you might use more statistics than ML that you will use if you really want to do, you know, the best prediction possible. And if the phenomenon is known to be a success with machine learning, for example, you know, image processing, like on Facebook to detect the faces of people, it doesn't get better than that. Important notes, of course, trying a simple model first is crucial. So you might not want to try, directly a very complicated machine learning model. You need to try basic linear models at the beginning, possibly statistical model. And but you must be aware that still the machine learning models are interpretable and uncertainty is often extractable in some ways. Which means that I'm not saying here that machine learning is black boxes. It's just that the goal is prediction. Okay, a very last quick thing, data science related roles, because people ask me this, and I think it's like a question, what is the difference between different things? So usually this is the typical graph you have, and it's also related to, statisticians. You have a mix of math, software engineering, data communication. The data analyst will try to basically have data from a company and try to plot things, the revenue, etc. The data scientist will try to make models, and so it's kind of the data engineer, but the data scientist can want to communicate. The thing is, this is kind of true depending on where you are, but it can get much more complicated. A lot of companies have this kind of graphs, which, or this one, which is my favorite, like it's, you put everything, you put cooking also at the bottom. I've really seen, I know because I looked for jobs in machine learning, and, depending on where you are, the definition can get very, very different. Okay, so this is the end. What we have reviewed is the main idea behind machine learning, the frameworks, the tasks, the general strategies, so selection, evaluation, and the comparison with statistics, which basically are complementary things based on what you want to do. This is a summary I found of just the typical machine learning tasks and frameworks in the context of clothes, socks by colors. So I just thought it was an interesting summary, and I'm done. Next time, we'll see different algorithms for machine learning. Yay, this was long. I'm kind of on time. And references, they're there, so they will be on the slide. Okay. Questions on this?
So there is 2 questions from the chat.
Okay.
I don't know if there is here a question from the room. Okay, so the first question is from Professor Marquez Vidal. Should we always use the 75-25 fraction for the training and test set?
Yes, it's just a typical rule, but you might want to change it based on the size of the data you have. Some people use 80%, 20%. If you have a lot of data, you might want to use as much as you can as a training. If you actually have a huge amount of data, you might want to take an extra set just for validating the hyperparameters. So it's really based on the size you have, but it's just a typical rule of thumb that a lot of people take, 75-25.
And the second question, how should we do for dimensionality reduction?
Yeah.
How do you do usually PCA, wavelets, others?
Yes. Okay. So the main, the linear regression equivalent of dimensionality reduction is PCA. It's principal component analysis. It's a linear dimensionality reduction that just projects the data on the highest variance dimensions, directions. So yes, that's what I would do first, because it's really useful, and you can actually try to see, because there's linear algebra behind, you can actually try to see the size of the eigenvectors on each dimension. Basically, you want to know how much of the variance you captured in the components you take. So if you have data in 90 dimensions, if you project down to 2 dimensions, you might lose a lot of data. So you want to know how much variance you get. So you might want to project in 10 or 15. But yes, PCA is very useful. If it doesn't work, meaning that you might not have a linear pattern, you might want to use nonlinear PCA, which is called kernel PCA, which is the next thing I would use. Otherwise, we have another linear one that's called multidimensional scaling, which is also quite a famous one. that you might want to try to use. But we'll talk about this in the next session.
Chiara?
So thank you for this enjoyable presentation. I was with you all the time. I'm not sure I got everything, but
Okay.
this is on me and not on you.
Yeah.
I have to admit, I'm a big fan of raw data knowledge. I mean, if I don't know who collect the data,
Yes.
how, when, I'm not listening to the stats. And
Okay.
it's funny because we were discussing this with a friend yesterday, and the problem, I mean, I think you're familiar with the idea that if you call the American Airlines and you have to talk in the phone, they don't recognize your numbers because you have an accent. And
Yes.
in your Alzheimer example, my mother language is Italian. I speak
Yes.
much more faster in Italian than in English. I can
Yes.
tell you, it's true story. And
That
you
makes
know,
sense.
and you know that facial recognition is not that good with not Caucasian faces.
Right.
Because the data set is flowed. So my question is, you need big data to do machine learning. So
Depending on the algorithm. You need
That's
good
it,
data.
yeah, that's the problem.
Ideally, you need good data.
Yeah, that's the question that I have. So how there is a critical mass of data, and in this critical mass, is there a standardized procedure, I don't know what it is. Anyway, a standardized
Yes.
Procedure.
Procedure.
Yeah,
Yes.
to evaluate the quality of the data, not just at the end of your, because if you come at the end of the
Yeah.
specification with a big problem,
Yes.
they need a prediction of people in the US who needed
Right.
more health assistance based on their health expenses. And
Yes.
then they know that afterwards that there are people who does have a lot of money to spend on health assistance, they weren't getting the cure they needed. So you
Right.
can make big mistakes. So
Yeah.
how do you evaluate the quality of data?
It's hard. Basically, depending on what you want to do, in any case, the first thing I would look at is how heterogeneous your data is.
Okay.
So you might want to, you want to capture as many features as you can in terms of range, in terms of variety, and kind of an equal amount of the same classes. So you know that, for example, if you have, 10 patients in your data which have Alzheimer's and 1,000 which don't have, you're going to have a problem. Okay, it's called imbalanced data. You have methods to do that, to try to do that, algorithms, but it's not going to get very good. And also you want to try to have the features that are as heterogeneous as possible so that you can cover as much as you can. And you want to do this also within the training and the testing. So in the training, you want just kind of the same proportion of the two classes and a good heterogeneity, and in the testing as well. On top of this, you can do a kind of cross-validation with the testing. So you might want to, for example, you have, 1,000 points. You might want to do, a test set prediction, so you measure the performance of your model multiple times. So let's say you take, usually when you do 75%, 25% of the data, you do it randomly. You do it once, but you can do it 10 times and kind of average the error, so that you have, again, as much variety as you can in your data. But yes, if the data is too small, or if you don't have enough variety, usually it's not quality data. That's.
If I may just complete.
Yeah.
It's not because you're doing machine learning, which is analytical methods for the data, that you don't have to respect to the research methodology. You have to really build a good proposal, to have a good data collection, and this is the primary things to analytics, and this is the same for statistics and for machine learning. This is, I would say, just a methods for analyzing data. So you can correct for biases, for some outliers and so on, but it's the same for other projects. And of course, the problem is, I would say now in the literature, you have many people doing predictions. And you see a lot of paper with data that indeed are not always very well challenged. In particular, doing external validations of your models, doing the same the same study on other data sets and repeating the research. But they don't really publish the internal validity or external validity metrics of their researches. And I have read recently a systematic review on predictive scores for, I don't remember, hemorrhages or thrombosis, venous thromboembolism after hip or knee arthroplasty. And there were many observational studies that were performed using statistics or machine learning, and no metrics on the calibration of the models, performance in terms of ROC curves, or even external validation were performed. In 6 papers cited, there were no metrics. So I would say to get more confidence in such models and in such data analysis, now providing the metrics that statisticians usually provide to prove that their models are reliable should be also provided in predictive modeling publications. Sorry.
Yeah.
So just to complement, it's of course you can correct the model during internal validation, but you should also do external validation on other data sets, as for any kind of modeling.
You need to have this data, but yes, that's
but you should try to do
definitely.
Eric?
I think a problem that is somehow related to the quality of data is missing data. I mean, that's a problem that we always deal with when you have real world data is missingness. And then I would say in classical statistics, you would have techniques like imputation before you go to any modeling, regression modeling, and so on. So with regard to machine learning, is there any approach in machine learning that is helpful or that to deal with that problem, other than what you would do with, for example, with different imputation techniques?
Right. Not really. I mean, missing data, you really want to use, typical methods that were used for many years, expectation maximization. You might want, if you really have a very, very small number of missing data, you might just take it away. But if it's a, significant part, you might want to use imputation methods.
So you would need to do it.
You would need to do it before
you go
to
any applying any of what you have just presented.
Yeah, definitely. Yeah, it's not a separated thing. It's just it's always valid. It's not because you do machine learning on top of it, rather than GMM or whatever other method that you would not do it. Of course. Yeah.
Could you provide a few examples of tools that can be used to visualize high-dimensional data? I guess when you have really very complex data, is to know basically what's in there.
Yes.
To try to understand a bit more, even if you can get out some prediction results that if you want to describe and visualize data, what are the most commonly used tools?
Yeah, so I would say you have kind of 2 directions. Either you use, kind of dimensionality reduction method, as I said, to just see the raw data, but in a lower dimension. So usually in 3D, everybody does it in 2D, but actually in 3D, sometimes you can really see good things, depending on what method you use. The problem is there are a lot of different kind of methods, non-linear methods, etc. So it might get complicated. But on top of this, you might want to put the data in a different format, of course. So you always have, typical statistics, of course. So just descriptive statistics, you would just see. Usually you do it anyway. Before you do machine learning, you would plot some, box plots, some histograms to try to see, again, the variety, etc. Then you might have other kind of visualization ways, like, graphs, for example. You might want to connect the data with different kind of relationships to try to see. I know that there's a lot of data visualization people that try to make a lot of, graphs to see the relationship between the points. But on top of this, some dimensionality reduction techniques are more designed to try to visualize it in the best way possible. this is the case of the one I show you with the handwritten numbers, which is called TSNE, which is a probabilistic method. It really tries to, have the best visualization possible, even though mathematically it's a bit rough sometimes. But yes, on top of my head, it really depends what you call complex data. Is it you have a lot of dimensions, you have a lot of points, or you have a lot of different possible patterns? Yeah, so I would try to reduce the dimension. I would try PCA and just go from there, basically. And of course, descriptive statistics, but that's always something you should do.
Patrick.
Thank you for your talk. For me, it's as a statistician, I'm quite happy to see that actually machine learning is statistics. It's simply, well, in statistics, depending on the goal you have, you will use different tools. And this belongs to, I would say, the toolbox of prediction.
Yes.
This is basically statistics. And so machine learning is simply statistics, but limited to the toolbox of prediction. Because all the methods
I see what you mean.
Presented,
but it's another way.
A long time ago already in statistics, and you mentioned in the 1960s.
Yes.
I think you were mentioning the book from Statistical Learning from Friedman and colleagues.
Yeah, sure.
These are statisticians, and
yes,
actually the nice thing, there is no dichotomy between statistics and machine learning.
Yeah. There's no.
These are different goals in statistics.
Yes.
May I distinguish prediction from causality and from description? And causality, it's usually what you are interested in, say, epidemiology.
Yes.
Description is what you do if you do know what you don't. Well, your goal is not to target a specific causal parameter, but more to describe relationship between variables. And the third one is prediction. And I think the novelty here is, thanks to the computing power, nowadays we can envisage larger models, and we are able to do the computation, which takes lots of time, and apply these prediction methods to typical problems which maybe a couple of decades ago, the computing power was not enough to envisage this kind of questions. But nowadays we have this power, and so we can take these old tools and apply them to say new data sets. And I think the difference is, there is no difference with statistics. It's simply a new, prediction. We have identified a lot of questions which can be answered using prediction models. And this is why it's so, nowadays, topical to talk about machine learning.
Yeah, but I agree with you. It's basically what I said. I didn't say that it was I didn't make a dichotomy. I just said statistics. So this statistician, Friedman, etc. Yes, they were statisticians, but they created another theory to try to optimize prediction. So they created new models, etc. But it's still based on statistical models. Yes. So it's So they're not separated entities. They're just, one is kind of the advanced prediction causing of the other. But
I just want also to react, but in a very practical manner. Imagine that you have, 50 variables in the model, and you just have not enough data to optimize your regression.
Yeah.
Then you can try these kinds of machine learning methods, which are still a numerical solutions. Just you reduce some, you minimize the difference between the predictions and the observation. So
you have a bit
fewer
hypothesis.
But in the same way, we've done this for a real project. We use machine learning methods.
Yes.
And some regression classical regression method, logistic regression in particular, and we confronted this with more or less sophisticated machine learning methods, and we finally found that the logistic regression had much more power in that case because we had few data.
Yes.
The training set was very, very small, and also we had unbalanced data, meaning that we have a lot of zeros and a few ones, a few cases. So there is no, I would say, there is no truth about statistic versus machine learning. There are solutions for more, as Dan said, for big or small data sets, for unbalanced or balanced data, and this depends always on the research question and on the quality of the data, of course, and the number of predictors. If you have 4 predictors, of course, it's much easier and efficient to go into a simple regression. If you have 50 variables, doing regressions with 50 variables and knowing the clinical meaning of associations of predictors is probably useless and meaningless. So having a good prediction instead is very important for an external validation set. And this what I took time to understand. The use are different. Sometimes I wanted to fit statistics into machine learning, and I couldn't understand why we could not apply the parsimonial rule, some metrics to assess the validity of the models, but they are not the same objectives. Mostly I use statistics for fitting the data, having learning associations or causal relations between the variables and the outcomes, and not prediction. In that case, it's only predictions, and what we want is to have the best predictive value, not reduce the number of parameters in the model, or having meaningful or clinically meaningful predictors. This is much different. We want to fit the data as close as possible to have, well, as best as possible to have the best predictions. So now a best outcome, predicted outcome, not the best predictors. The best predictors in the sense of doing the best prediction, but not in the sense of having the fewest predictors and the more clinically meaningful predictors. This is much different. And this is important because in some cases you can have risk scores which predicts some outcomes, which have 50 variables inside, which are perfect to predict, but totally useless for clinics, because you having 50 variables to inform, to predict the outcomes, it's too much. Or you have to automate this in your information system. But if the clinician asks 50 questions to the patient, then it's better to do the clinical interview, the usual clinical interview. So well, it depends on the research question and on the expectation of the tool. And this is for prediction, I would say. Am I right, Dan?
I think so, yeah.
Thank you.
Definitely.
So is there any other question? So thank you, Dan, for presenting. And next week or no? 2
No,
weeks?
it's 2 days ago. The next one.
Oh, 2 days. So
Yeah.
next time, Valérie will introduce
Okay.
the next presentation, and we will have then Dan and then Rémi Sabodadière.
Which is in 2 weeks.
In 2 weeks.
Yes.
Thank you for attending the presentation.
Thanks.